In these sections, we're going to look into the called the static indeterminacy. So what this is defined in principle is the number of unknown reactions is greater than the number of equilibrium equations available. Okay, keep these things in mind, and we have usually, again, here's the definitions. So here, if we have more numbers of reactions than available equilibrium equations, and we won't be able to solve for individual and each of the reaction force or moment. So we need more equations to help us to solve for the unknowns. And those equations basically come from what we call the compatibility equations. And the compatibility equations, basically that is regarding observations, very smart and good observations of the individual problems, and on the configurations of the geometry, boundaries, conditions, etc., and hopefully to make these things compatible, and that usually making up the compatibility equations is usually is the challenging part in solving this kind of the indeterminate problems. So in these sections, because of these reasons, I've tried to from different textbooks to summarize various types of the indeterminate problems that appeared in fundamental mechanics of material class. Okay, so here is the kind of schematic drawing. Here is a few types, and then in these sections, I'm going to split the lecture videos into a few video clips, and each of the video clips basically dealing with one type each time, and hopefully this small short the maybe less than 5 to 10 minutes of the video clips can bring you more detailed explanations of each type of the problems and then the solution strategy. Okay, so let's start with the first type. Basically, the first type is about the problems that's supported with a level. The features of this problem is this level is rigid, and rigid, that means that does not deform. Okay, it does not deform, but it can level, so can be level like this. Okay, so for this example, this level could be something like this one. Okay, be declined after deformed. Okay, such a rigid level only play only one role in transmitting force through this level to individual points of interest. And here for this support, AB and CD are deformable, which means our Hooke's law and our learned stress analysis applied into AB and CD. So that is this question here. Okay. Here, this rigid CDB, this one perform as the rigid, doesn't deform, but it declined. Always it remain as a straight line. So basically, this provides us a hint to formulating additional information for solving the problem. So we can start with this problem itself. So for each link of the link ABCD, and we have the given material properties and the geometries, and BD is rigid again. So we only have the applied loading 30 kilonewtons. So basically this tract is to carry a certain load, and that load applied to point E here. So here the problem is we want to find the deflection of BDE deflection, that means the vertical displacement, so we call deflection. So basically we want to find the vertical displacement of BDE in this system here. So the first things we like to start with is we take a free body diagram of this rigid portion, okay, and from here that is a plug loading, and here that is the action reaction taken from the pin where that linking to the deformable object. So here we assumed the reaction here is FABCD and in such assumed direction. Again, here you can assume opposite direction. No, sorry. You can assume the opposite direction. For example, if you like, you can assume FAB pointing downward, FCD pointing downward. Again, these assumptions is arbitrary, really up to you. However, once you make up your assumptions, keep your calculation consistent with your assumptions here. So let's take this assumed direction in our calculations. So here you can see there's two unknowns, and from here we can have the equilibrium equations. One is the equilibrium equation of the force in vertical direction equal to 0. So from here, for example, here you can see FAB and plus FCD equal to 30. Okay, so that's the equation 1. The second equation you might try is, say we take the moment about point B equal to 0. So take the moment about point B equal to 0. So that means 30 times this arm, 0.6, and should be equal to FCD times that arm, FCD times 0.2. So from here you can solve for FCD equal to 90. So with this one in mind, then we can solve for FAB, and that equal to -60. Okay, and here the textbook solution they using take the two moments, but either way. Okay, so right now we have solved the reaction here, then we move on to the next. So that is our original problem statement, and that is the free body diagram we solve for FCD 90 and then FAB is -60. So here, based upon the assumptions of FAB, assume upward we got a 60 minus, so that means FAB in reality is on this free body diagram is pointing downward and the magnitude is 60 kilonewtons. Okay, and I like to keep all the I like to work on positive numbers. Okay, so basically here will be maybe easier for the follow-up is if you like you can just change the direction to point downward with certain positive numbers here. Okay, and for this one the same, we keep the same thing as 90. Okay, so from here this is the free body diagrams, and then let me so here we take the free body diagrams of this one. So right now I take the free body diagrams and let me draw that free body diagram here. Okay, so here is pin B, here is pin B. So here this is the action reaction. So at the pin B in this is 60, so that means on here must be 60 kilonewtons in these directions. Okay, because to pin B the same thing, that is the action reaction. Action reaction, that means the same magnitude but opposite direction. So from here we determined the force applied to length AB, and on the other side A is here, and again in this whole free body diagram that is action reaction must be in equilibrium, so the force here is 60 kilonewton. Okay, so that is we have this case here. So under these situations, can you see we can determine the deformations of, say, point B. So for this case, because A is fixed, and then the deformation will bring B move to here, so that is the deformed displacement of point B, and that is calculated by PO over EA, and you simply plug in P here is 60 newtons, and LAE is the geometry informations here. So for delta B you can determine in magnitude equal to this, and then because it's moving upward, so here the authors of the textbook simply add minus here. Otherwise, you can say this calculation is 1514 millimeters, and you simply using the symbol indicating yourself is moving upward. Okay. And then displacement D here, and here we take the free body diagrams. For this free body diagram, again at the pin D, and that's the actual reactions, and here that is the same magnitude but opposite direction, because here in this free body diagram the point D is point upward, this is point downward, so that's a 90. So that's reason, and also on the top here the actual reaction here. So here that is 90. Okay, so here is come to here, and then we have this calculation. This is a magnitude, and from this case again, because point C is pinned and fixed against the wall, so that means this will bring up this calculation. The deformation is downward. So with this magnitude, remind yourself that displacement is downward, and here again at displacement B here is upward. We'll look into the next slides here. So here we have determined at point D, we calculated is downward, point B is upward. So here point B displaced upward to here, point D displaced downward to here, and again this BDE is a rigid. Let me use the different color here. Because BDE is a rigid link. So rigid, that means always remain as a straight line. So here remain as a straight line, that provides us a hint to as the compatibility equations. So from here you can see basically the triangle. This triangle is in proportion, in similarity to this big triangle. Okay, for example, using this kind of similarity, you should be able to take the proportionality of the size to determine delta E. The detailed calculation is showing here, and that is the answer.